of all, so first thing we need to make it clear of then about ionic lattices and molecules. Molecules are only ever covalent. You can't have an ionic molecule. Okay, it's worth saying twice. You can't have an ionic molecule. There's so many times I've heard people actually say just refer to ionic molecules. It's just that's not what happens at all. So let's just write that down then for your own notes. Molecules are always made using covalent bonds. That's the first thing. So we still don't. That doesn't really explain what it is, though. So basically, let's just get this one. Okay, no, that's not what I want. So a molecule is a group of atoms joined together, like chemically bonded together. So if we've got, let's imagine we had an oxygen. We'll get a few atoms together. Okay. So that is two oxygen atoms stuck together, or bonded together, I should say. Okay. So that is an oxygen molecule, all right? And so they stick together. There's going to be many of them, of course, in different rotations and so on. But so that's an oxygen molecule. Now, obviously, we know there are other molecules as well that exist. So you can also have water molecules. H2O. So yeah, I'll make a water molecule. Okay, so there's my water molecule. So a lot of people confuse molecule with compound for a start as well. They don't have to be this. They don't have to be different atoms. They don't have to be the same, but they are bonded together. Okay, so we're trying to understand what is the difference between molecule and lattice. So I've explained what molecules are: a group of atoms covalently bonded together. Okay, so this is a molecule. That's a molecule. Now, each individual molecule does feel attracted to the next molecule, but weakly so. So this molecule will be attracted to that molecule slightly, but not that much. Incidentally, water is more attracted to another water molecule for other reasons, more complicated reasons, which you may not learn about at GCSE, but it's called hydrogen bonds. Have you heard about hydrogen bonds at all? Does that ring a bell? Probably not in GCSE. I think in some GCSEs it gets covered, but anyway. So forgetting about hydrogen bonding, then this water molecule is not really very strongly attracted to that water molecule, and this oxygen molecule is not very strongly attracted towards that oxygen molecule. But within each molecule, the atoms are very strongly attracted to each other. So because what's happened is there's a sort of sharing of electrons, which you've learned about when you did covalent bonding before. And this sharing of the electron causes the atoms to be strongly attracted, sort of connected and bonded to each other by that sharing of the electrons, without going into too much detail. So how is that different to a lattice? Well, the big difference is with an ionic lattice, you're not sharing electrons, you're giving and taking electrons. So you're making positive and negative ions. So let's imagine something like sodium chloride. Now, if you looked at sodium in the periodic table, it's in group 1. So if it reacted, it would lose 1 electron and therefore become positive. Chlorine is in group 7, so it would gain 1 electron and become negative. So they would have a 1-to-1 relationship. A sodium ion and a chloride ion. So if we got, so let's draw a sodium ion then. So we'll make so we'll do Na. Well, Na, and I'll do a plus it like that. Okay. And make it a little bit bigger, bold, and we'll put it in white. And then we'll have chlorine, which we'll do in blue. Like that. Okay. So they're attracted to each other, obviously, because it's positive and negative. That is not a molecule. Why is that not a molecule? Because if another one of these came by, then the sodium is going to be attracted to the chlorine, like that, very strongly, just as strongly as that one is. So each sodium is attracted to the chlorine just as much as the next one. So there's no reason why they should separate into any groups. And in fact, even when I said, oh, if this came along, it wouldn't just come along like that, because they don't arrange in pairs in the first place. But they just basically gather into this sort of pattern. So these ions, they sort of collect together into this pattern, and this pattern of this arrangement is what we call a lattice. So it would just sort of multiply. Like if you get like a sort of grain of salt, which is sodium chloride, then it would. And if you're able to look closely enough, you'd be able to see the atoms arranging themselves like this. So I'll just add a few more. It looks like I'm recording my screen at the moment using Screencastify, and it looks like my internet struggles when I do that. When I'm using Miro and Screencastify, it does struggle. Anyway, so this is our lattice. Okay. Now, often it's just drawn as plus minus, but I've done it like this so we can just remind ourselves. What I find a big barrier of learning with ionic lattices is people often confuse the plus circle as a proton, and they feel like, oh, wait a second, I'm confused now. Are we drawing a nucleus now? We're not drawing a nucleus. We're drawing ions arranging themselves into an ionic lattice. Okay. And that is the pattern. Now, this is a simplified ionic lattice. They don't, generally speaking, arrange themselves in this crisscross pattern like that. And more to the point, it's actually a two-dimensional lattice, isn't it? We're drawing on a two-dimensional piece of paper, so in reality, it's three-dimensional. We can have a look at some ionic lattices. Ionic lattices. Okay, so I'll grab a couple of simple ones and maybe some more complicated looking ones. Oh, they're all pretty simple looking, actually. There's a slightly more complicated one. Okay. Now, how simple or complicated they are basically depends a lot on the relationship between one atom and the other. And that depends on the charge of the atom. So I don't know what's going on here. I mean, it's a bit difficult to make sense of sometimes. But so yeah, that one is essentially that one. They're just using a different way of representing it. But that's our sodium chloride there. And you can see that obviously one of the atoms is larger than the other one. So that's an ionic lattice. It just goes, and if another sodium ion came towards this lattice, it's going to be attracted to it just the same as all the other previous sodiums and chlorines. Okay. So a lattice goes on and on and on and on and on. Right. What about other types of lattices? Can you have a non-ionic lattice? You can't have an ionic molecule. Can you have a covalent lattice? Yes, you can. So how is it possible to have a covalent lattice? Well, diamond is a covalent lattice. So let's think about what do we know about carbon bonds? Well, from when you look at organic chemistry, you get told or showed or reminded that carbon has 4 bonds. Again, we're drawing in 2 dimensions here. So methane would be drawn like that, but only if we lived in 2 dimensions, which we don't. We live in 3 dimensions. So it's kind of like a representation of methane. If we actually got a picture of methane, you would use the 3rd dimension. So if I methane molecule, so there's a methane molecule. So this is in 3 dimensions now. So it's spreading all 4 electrons. There it is, and along the three different dimensions. Okay, so that's what it is in 3 dimensions. Now, if you imagine these 4 bonds of the carbon actually being connected to just more carbons and going on and on and on, then you'd have a never-ending sort of molecule in a way. So diamond, I'll put diamond structure, and you may have seen this before. It looks like this. Oh, I grabbed the wrong one. Okay. So this is a lattice. This is a covalent lattice. Okay, it's or often called a giant covalent lattice. It just means giant because it's just carries on going forever. There's no end to it really, and this is also why diamond is so strong, because one diamond is like one whole entire molecule. You can't call it a molecule because it's not a self-contained unit. Like if you look at the carbons at the edge, this carbon here only has 1 bond. So it's got these spare bonds on the end of it. So, you know, if there was any way of joining more atoms, we'd be able to join them to there. So it's not actually a molecule, but in many ways it's like a molecule because the bonds that are between the atoms are still covalent bonds, and so it's extremely strong. So in that sense, it's a little bit like one giant molecule. There are other giant covalent structures. Diamond is the strongest because most of the atoms are all bonded, apart from the ones on the edge. But there are, if we look at graphite, which is often the other one that's mentioned, it's probably one of the most common one mentioned in exams. Let's take a picture here, and in fact, if I take that one there, and let's take, what's a good one? I'll take a few, and we'll see what looks best. Okay, so yeah, let's look at this then. We'll, if you have a look closely, you can see that the carbons in each layer have only, the ones in the middle only have 3 bonds taken up, and the 4th bond is like this dotted line, and that's connected in a way to the layer above it. But the reason why it's dotted is because there's no preference to it being connected to one carbon or the other. So it's like as the layers slide over, and the carbons connect to this one, then connect to this one, then connect to this one, and so this means that the graphite is quite sort of flaky, and so you can use it for pencil lead. So it's sort of soft and it comes apart. And when you get a piece of graphite and rub it onto a piece of paper, it leaves behind bits of graphite, and so you can write with it and draw with it. But what else? What other properties does graphite have? Well, because it's got this bond that can like move from one place to another. When it's doing that, these electrons that are making those bonds occur are jumping from one place to another, and these electrons then are freed up to conduct electricity, and so graphite can conduct electricity. Diamond cannot, graphite can. Okay, so properties of graphite are that they can conduct electricity, and they're shiny as well, much like the metals were shiny. Again, we don't really go into the reason why free electrons make metals shiny, but they do, and that's why graphite is shiny too. Let's just jot down those properties there. So shiny relates to it having 3 electrons. Again, we don't look at that in too much detail, the reason why, but yeah, that is the case. And it conducts electricity, and it's flaky and soft. Okay. So that's really the main difference. That's really all there is to know, I guess, about the differences between molecules and lattices. You can't have an ionic molecule, but you can have a covalent lattice. All right.